Hello, and welcome to Lecture 5, where we're going to discuss vectors. This is going to be our big introduction to vectors, a lot of upfront information that we're going to put to use throughout the semester. Okay? The most immediate information is going to be the material included in sections 3.1 to 3.4. That's the simpler material that focuses on vector addition, all right, which involves thinking of vectors as right triangles and taking their components. We'll be talking about that plenty. We're also going to touch on material that belongs in 7.3 and 11.1, but we're only going to focus on the math, not the physics. So we're not jumping ahead. We're just going to cover the math. So we'll see it now, and then we'll see it again. And that's going to involve vector multiplication. Okay? And of course, this is a lecture that is for Survey 10th edition. Okay? So let's get right into some key terms. Well, our first key term, I actually don't have a space for, so let's define it. And that is, what is a vector? Well, a vector is a mathematical quantity with both direction and magnitude. It is usually represented by an arrow, like this F vector here. And we can see that that arrow has the criteria that define a vector. It has some length, that would be its magnitude, and it has a direction. In this case, the direction is shown relative to the x-axis by the angle theta. Now we could define it relative to any axis, okay? But this would be a full definition of the vector. We'll see there's notation that allows us to express the vector in a number of ways, but one way would be, the angle and the length. That would be F, okay? Notice that when we have a vector, besides drawing it as an arrow, when we write it, when we type it, we write the letter with a superscript above it that is as arrow itself, okay? So in formula form, you always see an arrow above the vector, okay? If there's not an arrow, it's not a vector. All right, so let's get into some mathematical rules about vectors, namely the commutative law and the associative law. All right, well, the commutative law simply states that A plus B equals B plus A. The idea there is that the order that you add vectors, because notice the operation here is addition, does not matter, okay? All right, so there you go. That's the same for numbers, isn't it, right? 5 plus 6 is the same as 6 plus 5, for example. Okay, well, what is the associative law? Well, the associative law says that you can group vectors in any way prior to addition. For example, I could add B and C first and then add A last, or I could add A and C first and add B last. It doesn't matter, okay? So the associative law is a lot like the commutative law. It just means you can group vectors, take care of them first, and then add other vectors later. Do note that the commutative law and the associative law both apply to vector addition. They both apply to that particular mathematical operation. What about vector subtraction? Well, subtraction is the same as just adding a vector multiplied by -1, okay? And multiplying a vector by -1 just turns that vector 180 degrees. For example, negative f would just be this. It would just be reflected 180 degrees, okay? So there's no special rules for vector subtraction, all right? Okay, so moving on. One way to conceptualize vector addition is the idea of tip-to-tail addition. This is just a graphical tool. It's not something you would really use to get a quantitative answer, okay? We're not really using rulers and protractors to get accurate estimates. This is just a way to get a rough estimate if we kind of need to think about where vectors are. I always support drawing a picture, and this is no exception to that idea. Draw the picture, it helps you understand the problem. All right, so what is tip-to-tail addition? Well, tip-to-tail addition is a graphical representation of vector addition, okay? For example, if I had a vector A plus a vector B, I could then graphically represent that by taking the vector A, writing it just like here. In this case, I've physically copied it or digitally copied it using the tablet, and then added B so that the tail of B, I'll zoom in a bit, the tail of B, which would be this point here, touches the tip of A. See, that's the name, tail, tip. This would be the tip of B, all right? So it's tip to tail. The tip of A touches the tail of the next vector. But the order wouldn't matter, would it? I could add B to A. All right, I could do B first and then A, and I'd get the same result, this time called C, represented as a green vector, right, the longer arrow. All right, so That means that tip-to-tail addition is sometimes called the parallelogram rule, since the associative rule or associative law gives us a parallelogram when we consider both cases of either a plus b or b plus a. All right? Now, we can also add three vectors together. Obviously, it doesn't just have to be two. I could add a, b, and c. So here it would be a tip-to-tail addition with a, b, and c. And then the result of adding all three of those vectors together we'll call r. And then just to show that the associative rule works, I could add a to c and then b and, well, still get the same r, right? Pretty neat. And I could even then define a new vector that's a plus c, call it d, add d to b, and I'd still get r. And that would be the associative rule. And with the previous one, it would be the commutative rule by just changing the order. All right? So that's tip-to-tail addition, good graphical representation of vector addition. Okay? Now, one big thing that we need to consider when we actually do quantitatively add vectors is how do we get the numbers? How do we get the quantities? Well, we do that with the idea of vector components. And vector components are just leveraging the fact that you can think of any vector, like the ones I've been drawing here, a and b and c and r and everything, as just the hypotenuse of a right triangle, where the legs of the right triangle lie upon some particular coordinate system, usually xy or xyz. Okay, so let's look at that. So a vector component is a projection of a vector onto an axis of any chosen coordinate system. All right, so that's a pretty broad statement. What does that look like in practice? Well, for example, the vector a is equal to ax plus ay. Now this is a vector equation here. All right, so the only way I could really do anything with this equation is just draw it. All right, so let's do that. All right, so over here I've drawn tip to tail graphical representation of the vector a as the sum of its x component vector plus its y component vector. Okay? All right. Now, this is word of warning here. This is not an algebraic expression that you could, like, say, do algebra on. You couldn't solve for a sub y by just saying that it's a minus a sub x. Okay? So a sub y is not equal to a minus ax. Why is that? Well, because these are vectors. That's why they have a little superscript of an arrow above them. That means I can't just change them into numbers. Okay? But of course I couldn't, because that would be the same as saying that, well, you know, that ax, if it's just a minus ay, well, that'd be the same as saying then that one side of the triangle, the length of one side of the triangle, is this equal to the hypotenuse minus the other length. Well, we know that's not true. We know we have to use the Pythagorean theorem. Okay? So that's the idea, that we have to go from a vector equation to an actual numerical equation, and otherwise we cannot do math. We cannot actually solve for anything. Okay? That may seem obvious, but I want to state it now to make sure there's no confusion on that topic. Okay? All right, so quick term to get out of the way, and that's the idea. Oh, actually, I want to further elaborate on how we would express the magnitude of these two components. All right, so ax would just be a cosine theta, or a sine phi. What is phi? Well, phi is an angle measured relative to the y-axis. Theta is an angle measured relative to the x-axis. There's nothing sacred about using theta as relative to x, nor phi relative to y. I may be in the habit of doing that, I may not be, right? Certainly theta is kind of the go-to Greek letter to represent an angle, and generally we do measure it relative to the x-axis because that's the way the unit circle is presented. That's the way that most of us are used to learning it in a math class, okay? But sometimes we certainly have a physical situation where it makes a lot more sense to talk about an angle relative to the vertical, all right? That's why it's good to have that flexibility, okay? Likewise, the magnitude of the y component vector of a is a sine theta or a cosine phi. All right? Now, where am I coming up with these sines and cosines? Just from the definitions of trigonometry. SOHCAHTOA, right? SOHCAHTOA. All right? The idea that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so now quick term to get out of the way. Resultant. A resultant is the sum of two or more vectors. It's simply the name we give to it. We usually represent it by the letter r. That's actually why I use the r up here to represent the sum of a plus b plus c. All right? So the resultant is just that name for that. Okay? All right, now on to the notation that we will primarily use for vectors. All right, now if you've seen it, it's great. You're like, oh, it's that whole I hat, J hat thing. If you haven't, it might seem a little strange up front, but it's just a way for us to represent vectors. It really makes the actual flow of writing problems, solving them, moving variables around, very practical in the ways that other notation just wouldn't be, okay? And also it's economical. I, J, and K, they're easy to write. We put a little hat above them just to denote what they are, and it becomes clear once you do it a few times. All right, so for example, we could write the A vector. We could think of it as the same vector as up here in the figure, all right? So we might as well think of it as that A vector as the component, the magnitude of the X component, that's just the length of this entirely horizontal vector, times I hat, whatever that is, right, plus the magnitude of the Y component, right, which would just be A sine theta, for example, times J hat, okay? So again, this is a vector. AX and AY, since they don't have the little arrow over them, are not vectors. They're just numbers. But what are I hat and J hat? Well, they have to be vectors because there's no way we could have a vector on the left-hand side of the equation equal to anything but a vector on the right-hand side of the equation. So I hat and J hat must be vectors. They must add together based on tip-to-tail addition to get A. But what are they? Well, turns out what I hat and J hat are unit vectors, okay? And a unit vector is a vector that has magnitude 1. Okay, so that's it. It's just the idea of multiplying the magnitude of a component by a directionality, right? Because I is just some vector that has length 1 that points exactly along the x-axis. Okay? J hat, on the other hand, is a vector that points exactly along the y-axis and has length 1 or magnitude 1, because of course length and magnitude are synonyms. All right? And the advantage of that is by multiplying by that unit vector, you don't change anything about the vector. You just make sure that your component points the way it needs to. In this case, the x component points along the x-axis and the y component points along the y-axis. But the advantage of the I hat and J hat, since they have length 1, they don't affect the actual length of either component. There's also another unit vector. Well, that one points along the z-axis, and that's k hat. Now, from this point on, we'll start introducing more 3D ideas of vectors. So you're going to see that a bit more. We haven't so much up to this point. You'll certainly see on the next page in regards to the key terms, as well as the equations, as well as the examples. There's going to be a bit more 3D. All right. So here we have k hat on the z-axis. And since this is kind of the turning point in this lecture to talk about 3D, let's draw a 3D axis. All right. So here we have x, y, and z. And here I've drawn the 3 unit vectors, I hat, J hat, and K hat. Now, the idea is I drew them kind of short to imply that they have length 1, that they're not very long. Okay? All right, so hopefully that is all clear. Let's move on to the next page. All right, so since we are talking about 3D coordinate systems, 3D axes, let's establish the idea that they have to be a right-handed coordinate system. All right, well, what is that? Well, it is a standard coordinate system that allows for use of something called the right-hand rule, which we'll talk about in just a minute. All right, so for example, x pointing off to the the right, y pointing straight up, and z coming out of the page, because you want to think of this as like kind of a 3D perspective, is a traditional right-handed coordinate system. Okay, x, y, z, and these are all positive x, y's, and z's. All right. Another one that you'll see quite a bit, not in our physics textbook, but you'll see in some other physics textbooks, as well as some math books, is this version of a right-handed coordinate system. All right, y, z, and x. Okay, so the idea there is that positive y is to the right. This one some people prefer because it shows z is up, and z is often thought of as kind of the vertical axis in a 3D sense, and then x is kind of coming out towards you. So and people do prefer this one sometimes because it has left, right for y, back, forth for x, back and forth, and then up and down for z, which kind of makes sense, right? Whereas here we're kind of almost saying that y is up and down and z is back and forth, okay? But this one is a little weird because we have to have y pointing off to the right, where typically in a 2D coordinate system, we're used to having it like this, right? And that's what's nice about about the way that I will be using, basically, I'm only going to be using this version of a 3D coordinate system because it's kind of a direct addition to just doing a 2D coordinate system with just x and y, okay? Now, these maybe just seem like they're just random coordinate systems. What makes them right-handed? Well, let me show you one that's not, okay? So this one here, x, z, and y, would not be a right-handed coordinate system. Why is that? Why does this one break the rule, right? Whereas these two are okay? Well, because every right-handed coordinate system is just a rotation of another right-handed coordinate system. So these two here can be rotated to go from one to the other. So I could take this one and just twist it around in a 3D sense to get this one. But I couldn't twist either of these around to get the no, breaking the rules, not allowed coordinate system over here. Because all I've done in this case is just swap, let's say I swapped x and y, right? I just swapped these two. Just swapping two axes without a rotation, you know, is violating the rule of a right-handed coordinate system, okay? All right, I know it's a bit to take in, but you have a couple of examples that I think give some concrete perspective about what I mean by a right-hand coordinate system. All right, so now into another couple big ideas, and that is what happens when we multiply vectors. So we just spent a while talking about adding vectors graphically, how to do it numerically by taking components, which will make more sense when you see it in practice in an upcoming example. But what about when we multiply them? Well, there's two ways to multiply a vector. We either multiply them together and get a number, which is called a dot product, or we multiply them together and get a new vector, which is called a cross product, okay? So let's look at that. So a dot product is a multiplication of vectors where the product is a scalar, okay? Now scalar is a term that I haven't used yet so far, and what is a scalar? Well, scalar is a mathematical term that just means a magnitude, but something that has no direction. So I've been trying to be very careful so far and always refer to scalars as numbers because after all, they are. So 5 is a scalar, okay? Speed is a scalar, velocity is a vector, okay? So scalar we have here is what you get when you take the dot product, when you multiply two vectors together. So you're getting a number. You're not getting a new vector, all right? So for example, the dot product takes the form of A, B. The operator actually looks like multiplication of numbers. It's just a dot, okay? It is associative, so A dot, that's how we usually phrase it. A dot B is the same as B dot A, all right? And then mathematically what it becomes is just grouping together the components. So A dot B, or the dot product of A vector and B vector is just ax multiplied by bx plus ay multiplied by by. And notice, right, none of these are vectors. So when I multiply ax and bx and then add that to the product of ay and by, I just get a number, all right? Because I'm just getting a scalar. Okay, but we'll get practice with that. What about the cross product? So the cross product is the multiplication of vectors where the product is a vector. All right, so this really makes sense, right? They're really covering all the bases here, right? We multiply them together, we can get a scalar, or we can multiply them together and get a new vector. That's it. Turns out there's kind of more to it, more implication, but this is a good starting point, okay? So it takes the form of A cross B. Okay, that's how we usually say A cross B. A vector multiplied by the B vector, or the cross product of A and B. By the way, it's not equal to B cross A, right? So unlike the dot product, the order matters. And that's actually brand new, right? Because so far, basically, all the rules of vectors have been the same as the rules of numbers. Associative law, commutative law, and the dot product work just like scalar multiplication. But all of a sudden, we get to the cross product and we have a new rule. Order matters, okay? All right, so we'll see more about the cross product in a minute. But let's define something called the right-hand rule. So for a given cross product, A cross B equals C. Okay, so we're getting a new vector from this type of vector multiplication. Okay, all right, and sometimes the dot product is called the scalar product, no surprise, and sometimes the cross product is actually called the vector product. Okay, but I'll be using the terms dot and cross. Okay, so A cross B equals vector C. All right, so the direction of C is defined by the right-hand rule. What does that mean? Well, first of all, before I even show you a figure of a hand, a cartoon figure of a hand, I want to just clarify something, and this idea we'll come back to. When you do the cross product and you get a vector as a result, that vector will always be perpendicular to both the vectors that you crossed. Okay? So, for example, C, this product of the cross product multiplication, is perpendicular to both A and B. All right? Now, what does that mean? Well, think about if A and B are vectors that are in the xy plane, then C must point in the z direction. Okay? If on the other hand, A and B are vectors that are in the xz plane, then C must point in the y direction. Get it? Okay? So, that's the idea. It's always perpendicular to both vectors. Now, if the vectors aren't in a nice plane, then it's kind of harder to imagine. You might have to, actually use a computer program to do it, or draw a careful picture, or just not worry too much about visualizing it. There is a limit to the 3D visualization where it can be more of a burden than a tool. Okay, word of wording there, but mostly a tool. But the right-hand rule can really help. It can really kind of give you that idea, and we'll get practice when we finally are putting this to physics, when we're really applying the right-hand rule for things like torque and angular momentum. We'll be actually using it a lot because we're going to have pictures that show things that are twisting and twirling, and we really need to think about the way the vectors point in that particular picture. Okay, gyroscopic motion is the poster child of really needing the right-hand rule, but we got a few weeks until we get there. Okay, for now, let's focus on the math and let's look at a hand. Okay, so I got a hand over here. Okay, this is from just Wikipedia. All right, and the idea is if I hold my right hand, doesn't work with the left hand. Okay, but if I hold my right hand and I use my middle finger to point in the direction of B, and I use my index finger to point in the direction of A, then my thumb will always point in the direction of A cross B. Not B cross A, but A cross B. All right, you see it? That's the right hand rule. You have to memorize that, okay? Because it can be kind of a burden to look it up. You want to have that really kind of at your ready to go in the back of your mind, okay? All right, so let's get back to the notes. All right, so a few key formulas I'm going to run through, all right? I want to get to the examples, so I won't spend a lot of time on these. The first one is something we already saw in the key terms. It's just the idea of taking a vector and breaking it into the components. Do notice that the components I broke it into both have a theta in them. So that means that I'm assuming that they're measured relative to the x-axis in the counterclockwise direction. That's the way that we would get a cosine and a sine. Okay? So that's just an arbitrary choice, but it's a common arbitrary choice. Furthermore, I have the magnitude of A. Notice the notation, two vertical lines on either side of a vector. That's how we denote a magnitude. Another way to denote a magnitude is just to write it as just a letter, right? So A with nothing is the same as A with vertical bars and an arrow, right? So you'll see me using both. And the idea here is that you just use the Pythagorean theorem to find that magnitude, okay? Now what if it's a 3D vector? Well, you will see this in the examples, but then we just have ax squared plus ay squared plus az squared, okay? We just add that third component, but otherwise the Pythagorean theorem would look the same. It would just be a sum of components squared all inside the root, okay? If you want to find the angle relative to some axis, in this case, the angle relative to the positive x-axis measured in the counterclockwise direction, then you could just take one component over the other. This is really just the definition of tangent, opposite over adjacent. All right, here we just have a 3D vector, okay? Just showing what 3D vectors look like with the I hat, j hat, and the k hat. All right, okay. Now finally, the dot product and the cross product, okay? So far I mentioned that the dot product is ax bx plus ay by. It's like just grouping together the components. And you can also put, and we'll see this in examples, az bz on there if there's a z component of either vector, okay? But another way to denote the magnitude of the cross product, which after all it is only a magnitude, is to write it as ab cosine phi, where phi is the angle between the vectors a and b, okay? These two results, so they look very different. A multiplied by b times cosine of the angle between the vectors is fundamentally equal to ax times bx plus ay times by, right? These are two identical statements, all right? And it's just kind of the beauty of what's going on, the way this mathematically works, okay? And notice that for the dot product, it's cosine of the angle between the two, all right? Now what about the cross product? So on the one hand, the cross product gives you a vector, but sometimes you only care about the magnitude of the vector that it gives you. So that's why I've just taken the magnitude. If I take the magnitude of the cross product, I get a expression that is really similar to the dot product. And again, I could call it the magnitude of the dot product, but that'd be repetitive because the dot product is just a magnitude, right? I just want to reiterate that. But anyway, so the magnitude of the cross product is the product of A and B multiplied by sine of the angle between the two. Okay, so big picture here. What does that really mean? Well, it means that a dot product is going to be biggest when phi is what angle? Well, cosine of 0 is 1. Oh yeah. So that means when A and B are parallel to each other, the dot product is just AB. Because it'd be AB times cosine of 0, which is 1, so it'd just be AB times 1, right? Okay. On the other hand, if phi, if the angle between them is 0, then sine of 0 is what? Well, sine of 0 is 0. So if the two vectors are parallel to each other, then the magnitude of the cross product is 0. Wow. So that means that the dot product and the cross product are opposites, right? One is maximum when the other is minimum, is 0, right? So when is the magnitude of the cross product largest? Well, obviously, when phi is 90 degrees. When the two vectors A and B are perpendicular to each other, then the magnitude of the cross product is just AB, because it would be AB times sine of 90, and sine of 90 is 1. Okay? So that's going to come up a lot when we start using it, because there's certain physical quantities that are maximum when vectors are parallel to each other, and there's other physical quantities that are maximum when they're perpendicular to each other. The big ones being work and torque, respectively. All right? But sometimes you don't care about the magnitude of the cross product, you actually care about the vector, and that gives us this, okay? So this arrow is coming down from the definition, okay? And this is just showing how to actually calculate the cross product, because it's a bit of a bear, okay? A good way to do it is to draw this little expression here. Technically, this is a 3x3 determinant, so it's a mathematical sort of expression that comes from linear algebra. But I really just use it as sort of a bookkeeping tool to remind me how to get this expression correct every time. And what I mean by that, I will show you with some colors here. All right. So the idea is that if I want to look at the coefficient or the scalar that's attached to I hat, then I just take AY multiplied by BZ, that's what this ellipse is, minus AZ multiplied by BY, okay? And then that is all attached to the I hat direction, okay? So this is just see how the colors match up? So the green circles match up with the green coefficient or the green scalar multiplied by the unit vector I hat, okay? And then I do the same thing for the J hat, but J hat is different because I'm going to do the same sort of thing. I'm going to take AX multiplied by BZ. Here I just kind of split the ellipse to show what I'm multiplying together. AX times BZ minus AZ times BX, okay? So those two. But notice that on the J hat, okay, on the J hat component of the cross product, there's a leading negative. There was no such leading negative on the I hat. And there's also no leading negative on the K hat. So the J hat is the only odd one out of the three. It's the only one that has a negative in front. And you can think of it as the only one having the negative in front because it is the only one that's split, okay? Because if we get to K hat, then we go back to drawing these full ellipses and following the same rule. AX times BY minus AY times BX, all right? And that one, no negative in front, okay? So the middle term, the J hat, is the odd one out and it has a negative. And you have to remember that, okay? Or look it up, all right? All right, let's finally get to some examples, get to some practice. All right, so the first few are going to focus on vector addition, and then we'll do multiplication. So there's three types. There's kind of naturally broken up into addition problems, which is type 1, dot product problems, which are type 2, and cross product problems that are type 3. Okay, so let's take a look at example 1. Two vectors exist on the xy plane. Vector A has magnitude 6 and points at an angle of 30 degrees above the x-axis. Vector B has magnitude 9 and points at an angle of 70 degrees above the x-axis. What is the resultant of these two vectors? So notice I didn't give you these vectors in I hat, J hat notation because I want us to get used to different ways of expressing vectors. In this case, I'm giving you the vectors by giving you their magnitude and direction, which is fine. That is a complete description, okay? So let's draw a picture. All right, so based on the information, I've drawn A, right, which is a shorter vector that is closer to the x-axis, and B is a longer vector that's much more vertical than A. Okay? By tip-to-tail addition, I know that r should point somewhere between the two, and it's going to have some angle relative to the x-axis, which I've chosen to call theta, right? And it's going to have some magnitude, which is just the length of that black vector. Okay? So what do? Well, first of all, I note that r is equal to a plus b. That tells me that the x component of r is just equal to the x component of a plus the b component of the x component of a plus the x component of b. Likewise, the y component of r is just equal to the y component of a plus the y component of b. Notice that these are not vector equations. These ones are scalar equations, okay? Because I've broken them into components. All right, so then I can write out the resultant I'm looking for in I hat, j hat notation. Even though the vectors I was given weren't, I can absolutely convert over. You can always go back and forth between thinking of them as lengths and angles or writing them in I hat, j hat, okay? And in doing so, you can see all I do is just group together the components. I'm getting the components, for example, AX. I'm just getting that from SOHCAHTOA, just treating A as a right triangle relative to the x-axis. Same exact thing for B, all right? So I'm treating them all as right triangles and all relative to the x-axis, okay? So this is more there, okay? Right? That's really a great way to do it. And again, nothing sacred about the x-axis. I could have made them all right triangles relative to the y-axis, but I chose not to, okay? That wasn't a very good right triangle. I'll try it again. There. Okay. All right. So then here I just have the y components. Same deal. Both the y components have sines. Both the x components have cosines. Right? No surprises there. Right? When I add everything together and I round to 1 sig fig, I get 8 and 10 for my r vector. And this is an I hat, j hat notation. Now, it wasn't specified. It just said, what is the vector? So if I ask a question like this, what is the resultant of these two vectors? I'm not asking for its magnitude. I would have said magnitude if I was. So it's totally fine to give me the answer in I hat, j hat notation. Alternatively, you could have given me the magnitude, but you would have also had to give me the angle relative to some specified axis. So you could have said, oh, well, the resultant has length 10 and has an angle of 50 degrees relative to the x-axis. In other words, theta is 50 degrees. Okay? So both of these representations of the resultant r are fine. That one or these two together. Okay? All right, let's move on to another one. Example 2. What vector must be added to A to get r? All right, so one's pretty straightforward. So I know that A plus B equals r. I've chosen to call the vector I'm looking for B. So then B must be r minus A. Okay, well then that's simply a matter of then taking r, right? So taking the x component of r, which is -6, and subtracting the x component of A, which is we subtract positive 12, so it's minus 12. Same thing for y components. And then for the z component, well, r has a z component, right? So of course attached to the k hat, okay? But A doesn't. So the z component of r is just left alone. It'd just be -2 minus 0, okay? So then my answer is just this, right? This is my desired vector. B is -18, positive 12, -2. So negative 18 in the x direction, positive 12 in the y direction, -2 in the z direction. But I decided to draw a picture because, you know, it's not always easy to draw pictures on these ones, but it's good to see it at least a couple times. So here's the idea, all right? So you know that A is entirely in the xy plane, right? So I've drawn A here, and we want to imagine this in an xy plane. Meanwhile, R is not, right? R has a negative x component, so that's why it's going back in this direction. It has a positive y component, which is why it's pointing up along the y-axis, but it has a negative z component, so it's going back into the page. A clever way of showing that, I think, is to do little dotted lines that make right triangles, because then you can really kind of then visualize that R is kind of going back into the page, all right, and then clearly ending up over in, you know, a region that's behind the y-axis. All right, you can kind of see that based on the dotted lines I've drawn, or do the dotted lines help, I hope? Okay, and thus B, which must point from the tip of A, all right, to the tip of R, okay, that B must then also go back into the page, which indeed we know it does because it has a negative Z component, okay? All right. All right, so moving right along, example 3, this is our first one with multiplication, all right? And from this point on, all of the examples are going to involve more multiplication, okay? Now, I mentioned this in the welcome video this week. You're not going to see multiplication in the homework. It's going to be a while until you're really working on multiplication with physics applications, that is vector multiplication. But the one thing you do want to be aware of is that this week's challenge problem does involve vector multiplication. So it's kind of a trade-off about how much focus you want to give it. But again, from this point on, all the examples in this lecture video will involve vector multiplication. Okay, so example 3. A displacement vector is given as r equals 12I hat minus 0.8j hat minus 4.4k hat. And a force vector is given as negative 3I hat, negative 22j hat, and positive 5.6k hat. What is the angle between these two vectors? Okay, now the reason we can find the angle is based on that definition of the dot product. Okay, so we use the definition of the dot product, which says that r dot f is equal to rf times cosine phi. And phi, after all, is the angle between them. So if we can just find a way to isolate phi, we're done. Okay, so, and then we're going to take the fact that r dot f can also be expressed as rx fx, ry fy, plus rz fc. So in other words, the sum of the products of the components. The sum of the products of the components. All right, and this is just a number. Okay, so let's do it. Okay, so the first thing I'm going to do is the sum of the products of the components. So I just take the negative 12 times 0.3, positive 12 multiplied by negative 3, right? No 0.3 there. Add it to negative 0.8 times negative 22, and then add all of that to negative 4.4 times 5.6, and I get negative 4.3. Yeah, lots of stumbling on my words here. Negative 43. All right, and then I'm going to find the magnitude of r. Why? Well, because this r right here, it's the magnitude of r. That's what it is. That's what r represents without a vector over it, right? There's no vector shown over r. Okay, so that means I have to use the 3D version of the Pythagorean theorem to find the magnitude of r. 12.8. Okay, do the same thing for f. 22.9. All right, looks good. Okay, so then that means that my whole equation here, basically setting this equal to this, see, is then negative 43 equals 293, and 293 is just 12.8 times 22.9 times cosine of phi. All right, well, now I'm ready. Then I'm just going to isolate phi by taking cosine inverse. Of course, I divide both sides by 293 first, okay? And I get an angle of 98 degrees. So these two vectors are almost perpendicular to each other, which you wouldn't know by just looking at them expressed in I hat, j hat, k hat notation, would you? All right, so pretty cool. We found the angle between these vectors. And you might be like, but wait, these are 3D vectors. What does an angle between them even mean? Well, it means this. Any two vectors, even ones pointing off in weird directions like this, form a plane, okay? A plane is formed by two vectors, right? That's all it takes to form a plane. Now you could have more vectors in that plane, but any plane is defined by two vectors, okay? So that means that the plane defined by these two vectors, along that plane, this is the angle between them, okay? All right. All right, so let's do another one. All right, so a displacement vector is r equals 12I hat minus 0.8j hat. Well, a lot like our previous displacement vector, okay? And then our force vector is negative 3 minus 22, negative 3I hat minus 22j hat. The only difference with these vectors is that neither of them have a k hat component anymore. Okay, so I've just completely got rid of the k hat component because I want to illustrate an idea about the cross product. Because we're asked here, what is the cross product between the r vector and the f vector? Okay, and I point out that later we'll find that actually crossing a displacement vector with a force vector is by definition torque, but a few chapters till we get there. Okay, so I'm just going to write r cross f. All right, I'll set up my little kind of mnemonic thing here to make sure I do my writing everything out. It helps me. Okay, well, if you think about it, well, everything attached to the I hat's going to be 0, right? Because if I do my little ellipses, I'm just going to have 0 times something minus 0 times something, and then for the j hat, it's going to be the same because it's going to be 12 times 0 and then negative 3 times 0. So everything just zeroes out. So that means that the cross product of r and f has no x component and no y component. It only has a k component. Oh, interesting, right? And so then we end up finding that it's negative 270 k hat. All right? No units because we're not worried about the units here, okay? So why is that? Why does it just have a k hat component? Well, let's think about it, right? So here's my coordinate system, x, y, and z. Now, the vectors, the two I was given, let me do this again. So x, y, and z. So the vectors r and f were entirely in the xy plane. right? So R and F were somewhere over here. Here's R, we'll say, and here's F, right? Just kind of making up their locations. Since they're in the xy plane, the only way we can get a vector that's perpendicular to both of them is to have that vector entirely in the z plane, all right? It has to point in the z direction, okay? That's the only way I can point, okay? All right, so because it's perpendicular to both of them. It's perpendicular to the plane formed by those two vectors, okay? All right, so moving on to the next example. What is the angle between a v vector and the y-axis, okay? All right, so this is really kind of similar to example 3, except instead of taking the angle between two vectors that are kind of specified as vectors, I'm specifically comparing it to an axis. Well, how do I compare a vector to an axis? Oh, just take a hat vector. In this case, since it's the y-axis, take the j hat vector and just take the dot product between my v vector and the j hat vector, okay? So I'm going to do v dotted with, I wrote I hat, but I meant to write j hat. Excuse me. So I'll go ahead and continue with I hat. I actually misread this as the x-axis. So it'd be a similar result. So here, I'm solving this problem for x-axis, okay? Take note of that. So then the only component that wouldn't be 0 would be that wouldn't become 0 is vx, and that's because the I hat component, and again, assuming that this is x-axis, the I hat component is just 1 along the x direction and 0 along the y and z directions. So in other words, v, y, and v, z, the components of v along those other axes would just be multiplied by 0. So they don't show up. The only one that survives is vx times 1. Okay? Meanwhile, on the other side of the dot product, I just have the magnitude of v multiplied by the magnitude of I hat, and the magnitude of I hat, of course, is just 1. Okay? So then I can just find the angle again by doing an inverse cosine. All right, and I've dropped my 1s here because multiplying by 1 on both sides doesn't change anything, not to mention it cancels. All right, and so then I end up with an angle of 51.1 degrees. Okay, so that is kind of the idea about, kind of finding this vector, okay, and comparing it to an axis. All right, so in the next two problems, we're going to keep thinking about unit vectors, but now we're going to think about unit vectors that don't point along a particular axis, but instead point in some other direction. Because I hat, j hat, and k hat are great, right? They're unit vectors, which means you can multiply them and not change the magnitude of whatever it is you're multiplying by them. But they're stuck on the particular axes of x, y, and z. What if I want a unit vector, a vector of length 1 that points, say, along a 45-degree line between a couple of axes, or just along some arbitrary direction? I can define a unit vector anywhere. The way to define a unit vector is just to divide by the magnitude of a vector. All right, so let's see what that looks like. Okay. All right, oh, and I point out in the previous example, before I move on to example 6, we can see that the dot product of v and I hat simply gives us the component of v parallel to I hat. It just gives us vx, okay? All right, okay, does that make sense? That this right here, the actual value of the dot product is just vx, okay? All right, so in other words, I just took vx divided by v and then put it inside the inverse cosine in order to get my 51.1 degrees. Okay, all right, so example 6. A vector A has length 16.4 and points along the xz plane at an angle of 45 degrees above the positive x-axis. What is the magnitude of the component of this vector that is parallel to the vector b equals 24.5 plus 44.7? Okay, so to define the component of a vector parallel to another vector, we use the dot product, just like we did up here, okay? But we need b hat, not the actual b vector, in order to not affect the length of A parallel, okay? Because we want to find just the length of A parallel to B. We don't actually want to multiply A by B, okay? We don't care how long B is, honestly. But we do care where B points, okay? All right. All right, so what does that look like? So we want to find the magnitude, because I asked for the magnitude of the component of A parallel to B. That's why I've given the subscript notation of 2 lines. This denotes parallel, okay? So by definition, that's going to be A dotted with B hat, okay? Which is the same as A dotted with B divided by the magnitude of B. Because this right here is B hat, This is how to turn a vector, in this case the b vector, into a unit vector. You divide by that vector's magnitude. Okay? So here's the vector, 24.5 I hat plus 44.7 k hat, divided by the magnitude. In this case, this is the 2D Pythagorean theorem. Okay? So then, now I actually go ahead and multiply out the components. So now I'm just going to multiply the a, because at this point, up to this point, I've just left a as a vector, but I can write ax times b hat x plus ay times b hat y. Okay, ax is just 16.4 times cosine of 45, okay, because it's just the x component of a. Meanwhile, ay is just 16.4 times sine of 45, okay? And at this point, we still have everything in vector form because we haven't actually finished taking the dot product. So the dot product would still be right there, okay? And then when we actually take the dot product, all the vector notations go away because, of course, we're just getting a scalar, all right? And then we just get 11.6 times 24.5, and then 11.6 times 44.7. The 11.6, by the way, is just 16.4 times sine or cosine, for that matter, of 45 degrees. Okay, you can check the numbers here. The 1 over 51, well, the 51 just comes from the square root of 24.5 squared plus 44.7 squared. So this right here, the whole denominator, is 51. Okay, and that gives us 15.7. All right, so pretty close to the full magnitude of A. Well, why is that? Well, let's look at the picture. Okay, so if I was to kind of do a rough sketch of A and B, B is much longer, all right, and it points up more than it's straight between x and y. A is shorter and is halfway between x and z, not y. All right. So then when I'm asking about the component of A parallel to B, I'm actually asking about this, right? I'm making a right triangle, right? There's my 90 degrees with one component that's parallel to B, a component of A, and one component of A that's perpendicular to B. See? That's all I've done. Okay. But the way I did that was with the dot product, which is actually a very, very fast way of doing it. I mean, are there other ways? Could you just do it with brute force geometry? Sure, okay? But using the dot product is actually a really nice way of finding this component, okay? And then in example 7, I say, okay, well, what is the component? So otherwise the problem is set up the same, vector A, same length, same angle between x and z, all right? But now I want the component that's perpendicular to the vector B. Well, some people might think, oh, well, wouldn't use the cross product in that case because dot product is all about things that are parallel. Cross product is always about things that are perpendicular. No. Because the cross product is about things that are perpendicular, but it's about things that are perpendicular to both vectors. If I took the cross product of A and B, I get a vector that's perpendicular to both A and B. I don't want that, right? Because this vector, the component A perpendicular, is definitely not perpendicular to A. It is only perpendicular to B. So A perpendicular, what example 7 is asking for, would not be found using the cross product. Instead, I would actually start example 7 the exact same way I solved example 6. All right, so I'm actually just going to move forward with that work. So the first step of the solution is identical to the full work in the previous example. All right, so I then assume that I've already found A parallel. I would then write out a vector equation saying that A parallel plus A perpendicular equals A, which we can clearly see from tip to tail addition of vectors over here, okay? And then, since they form a right triangle, I have A parallel squared plus A perpendicular squared just equals A squared, okay? Because they're a right triangle. So then I can just easily find A perpendicular, all right? And it's like this, by plugging in the numbers, and it's 4.6, much shorter, just like the picture suggests, okay? All right, so that is the component of A that is perpendicular to B, but still in the XZ plane. So that's an important caveat, right? But it is exactly what's drawn. All right, last example. All right, let's finish this up. Okay, so this is a final cross product example. All right, any two vectors form a plane. I've said this a few times, right? But here it is in writing. In this case, those two vectors are V and F. What are the two unit vectors that are perpendicular to that plane? Okay, so the cross product V cross F and F cross V will give us the two vectors. Okay, perpendicular to the VF plane. That's the plane formed by V and F. Okay, so, and by dividing by the magnitudes, we'll then get the unit vectors. So just like in the two examples ago, where we found B hat by taking the B vector and dividing by the magnitude of B, we're going to do the same thing here. Okay, all right, and furthermore, V cross F, we know it's not equal to F cross V, but here I'm telling you it's actually equal to the negative of F cross V. So changing the order of a cross product just gives you that negative, which is why we're going to get 2 unit vectors. And those 2 unit vectors are essentially going to point to either direction of a plane. So imagine like a sheet of paper, and you have one vector that's normal to that sheet, so perpendicular to the surface, pointing up, and then you've got another vector that's perpendicular to that sheet pointing down. Those are like the 2 unit vectors we're thinking about here. Okay? Okay, so let's write this out. So V cross F, all right, I'll do all the math, a bunch of like make sure our numbers work out, and we get the following vector, okay? And we're going to call that Q, okay? And then I'm going to find Q hat by just taking Q divided by its magnitude, okay? So there we go. I have a 1 in 80 that just comes out of the square root, all right? So thus our 2 unit vectors are just going to be Q hat, all right? And that's just distributing the 1 over 80 onto each component, okay? It's a vector because cross products give us vectors, all right? And notice that this unit vector has length 1. You can check and confirm that it does have length 1. And negative Q hat. And that is our answer. Our 2 unit vectors. Okay, so that's a wrap for this lecture. I know it's been a long one with a lot to take in, but thank you so much for watching. And ask me any questions about vectors throughout the week and weeks to follow. All right.